Get started in a minute. Hello.
Can I have an announcement?
Hi. When I get quiet, that's down. Hi.
So, before the colloquium starts, I know most of you are enrolled in CSCI 5100 and 6100. So just few comments. Attending colloquium is mandatory in person, right? Under special circumstances, we allow you to attend via Zoom synchronously with your video on. Then Maggie and me can also take your attendance. But for that, you need to coordinate with me. You need to send me an email, provide a reason why you cannot attend in person. Then we allow you to be via Zoom, but synchronously with your video on. The attendance will be taken using some card reader at the end of the colloquium, not in the beginning. You want to ensure you are sitting till the end. And the assignment for each colloquium will get lunch immediately after the talk. You have 1 week to answer, submit, in order to get the full credit. But of course, you have till the end of semester, but only you will get 75% of the score for that assignment. If you miss the due date, which is 1 week after the colloquium. So what else? I think I covered everything. Is there anything else?
Oh, so today, we didn't take swipes on the beginning of the class, so we'll do it at the end.
But we decided to do all the time at the end.
Okay, yeah, so today and all other days.
All other days is going to be at the end, yeah.
Today, we will be taking an attendance system.
Yes.
So yeah,
Okay.
so we'll be set up right here at the end to come by and swipe.
Out that door to leave.
Yeah, thank you, and thank you.
Okay. Okay, hi, everybody. To kick off our spring colloquium, we have Dr. Tamara Lehman. Tamara got her bachelor's degree in industrial engineering at the University of Florida, and then a master's and PhD in computer engineering from Duke. She joined CU Boulder in 2019 in the ECE department, but I know she has lots of overlap and a lot of collaborations with many of us in computer science. So we're really happy to hear her talk today. Tamara works on computer architecture and security, GPU side channel attacks, secure memory access, and more recently, misinformation and news and social media, among other topics. And today she'll be talking about secure, efficient, and high-performance computing from a computer architecture perspective. So thanks, take it away.
Okay, thank you very much, Rebecca. Okay, thank you for that warm introduction. So I guess she already covered about 2 slides that I already had planned. I want to tell you a little bit about myself because I always think it's easier to understand topics when you understand where they're coming from. So as Rebecca said, I started here at CU in fall 2019, and the classes I teach all surround computer architecture because that is what I'm passionate about. And realizing that the majority of the people in the room are students, I will encourage you to sign up for my advanced computer architecture class that I'm teaching this semester if you find the topics that I'm talking about today interesting. Today will be more about the security aspect of it, but if you're interested about learning more about computer architecture, I encourage you to sign up for the class. Okay, which is listed both in ECE and CS. All right, I'm gonna skip this part, which you already know my background. I was also born and raised in Argentina, something that Rebecca did not mention, so I'm gonna say that. So I speak Spanish, so if you guys also speak Spanish coming up, let's chat a little bit about in anything except technical in Spanish. I can't speak technically in Spanish. I don't know why, I just learned it in English, so that's how I talk. Okay, so that's my background. In terms of research, as Rebecca already told you, I am interested in the intersection of computer architecture and security. So I'm interested about computer architecture because I find it fascinating to really understand what is happening inside this magical box. I think it looks like a black magic, and like rats are running inside, like just on a little rolling pin, who knows. But actually I know, and that's what happens when you actually study computer architecture. You get to understand what is really happening when you write that first program, hello world. What does that mean? What is happening inside that little magical machine? And then I'm interested about security because, first of all, it's one of the most challenging problems in computer science. And I like challenging problems. And also because I think it's really important that all of our machines keep our data safe. And there hasn't been much work done on the architectural side of things, which is always fascinating to me to find an area where it's really important. Not many people have been paying attention because there was other shiner and prettier things to look at. And so I like to be kind of the oddball doing weird work that addresses a significant problem. Okay, for that reason, my research interest is in microarchitectural security, and I am interested in developing efficient and secure microarchitecture. All right, so in the past, in my PhD, I always focus on working on efficient, secure memory systems, which basically try to protect your data and memory from physical attacks. And there's a very narrow view of microarchitectural security. And so, of course, once I started my assistant professor position here at CU, I started to evolve my view of architectural security and into other attacks besides physical attacks. And so in my lab for the last 4.5 years, we've been developing systems that can prevent attacks from many different attack vectors. So we're looking at protecting against cache side channel attacks. We're looking at protecting against transient execution attacks and many more attacks that are really interesting at the architectural level. But besides architectural security, I have also expanded into using this knowledge that I gained throughout my PhD to also protect 5G communications by using the secure memory system concept. And in addition, I ventured even farther away from architecture into understanding the impact that technology has on democracy and societal issues as a whole. So that's a really interesting work that I've been doing with a couple of faculty in the CS department. It's been evolving into a very interesting line of work that I'm really enjoying. Okay, but that's not what I'm talking about today. Today is all about computer architecture and security. So I'm going to be telling you about the 3 projects that we're working on with my students, and hopefully I will get you interested into computer architecture and furthermore into security. All right, so why should you care about microarchitectural security? We should all care about this, not just me. And the reason is that we live in a connected world. Everything we touch, everything we do has an electronic device in it. And believe it or not, those electronic devices are not very safe. Nobody has been paying attention at the architectural level. So you may be thinking, well, what about security, software security? Isn't that enough? Well, not really, right? Because if you have a vulnerability at the hardware level, there's nothing you can do at the software level that will patch that. So that's why you should care about microarchitectural security as well. And in particular for me, I'm interested in this research direction because if you read the literature in the computer architecture community, you will see also in the security community, you will see very often 1 year, somebody finds a very bad vulnerability. The next year, it gets patched with some solution, the best and greatest defense mechanism. And then the next year, another vulnerability comes up that defeats that defense mechanism. And then we're here in this loop over and over and over. And then there's not much progress happening, okay? Well, there's a little progress happening. I shouldn't dismiss everything. There's a lot of progress happening, but it is not simply not enough. And my view of why we're in this cycle is that we're not targeting the root source of the problem. And many times the reason for that is that security adds a performance tax on the system. Like, raise your hand here if you've heard, oh, security will really damage your performance. I think everybody understands that, right? Most people understand. Give you something secure, you know that's not gonna run as fast. And that's a problem, because we shouldn't have to make a decision between performance and security. It's like asking you, would you rather drink water or eat food? You can't make that decision, right? It's not a reasonable ask. So I'm trying to actually look at a more fundamental level from the architectural perspective on the security issues and try to come up with defenses that are not eventually going to find vulnerabilities again. Okay, so the agenda for today, I'm gonna tell you about cache site channel attacks. Hopefully this is all new, so you don't fall asleep with me. And then I'm gonna tell you about one defense that we came up with, near memory processing. Then I'll tell you about transient execution attacks. And then I'll tell you about one defense mechanism that we're working on. And then finally, a monitoring infrastructure that we developed to identify this attack. Okay, so we'll go ahead and get started with cache site channel attacks. And of course, a lot of you have never taken an architecture class before, so I have this slide for you here. So if you are not familiar with how machines look inside, this is kind of a very simplified version of all the components inside a machine. So you have your cores where all the logic is happening. You have your caches at different levels that have both data and instructions. And then you also have your memory, which is the next level where your data can live. And cache site channel attacks, of course, like the name suggests, impacts all caches at all levels. There's been plenty of work that show that a cache site channel attack can defeat encryption algorithm, encryption keys by targeting different levels in the cache hierarchy. Okay. So this is the components that we're looking at for now in this attack scenario. Okay, so then for computer architecture basics, data and instructions are stored in memory, and then memory feeds the caches as data and instructions are used. So the most frequently used data and instructions are brought into the cache. Now, the cache usually has a cache hierarchy with different levels. And the reason why we have these levels is that the closest we are to the core, we can make the caches smaller so that they are faster to access and they can have the most recent data used. And then as we get closer to the memory, the caches are larger and then they contain more data, preventing that memory access. We want to avoid a memory access at all costs because memory accesses are really expensive. And to give you an idea of the difference in timing to access the different levels, the L1 cache usually runs around 4 cycles. The last level cache takes about 10 cycles. And then anything outside of that memory can take about over 100 cycles. So you can actually tell the difference between accessing data in the L1 cache, accessing data in the last level cache, or accessing data in the memory. And furthermore, generally, modern processors are multi-programmed. So when you're running one program, it's very likely that there's many other programs running at the same time. And in certain contexts, it can even be programs run from another user. And the cache state is usually not cleaned up when the context is switched between the users. And that's for performance reasons again. If you flush your cache, then your performance will suffer significantly. Okay, so with this in mind, I'm going to introduce a very typical cache site channel attack called prime and proof. So this is a cartoon version of that, but I will show you the code, more or less the code that you need to run it. So you'll see it's a pretty simple attack, but it is actually very powerful. So the initial state is that you have 2 users running on a processor, and they're sharing the cache. I'm just waving my hands at the cache hierarchy because it doesn't matter at what level it is. It's been shown that it's possible to attack at any level. And then the cache contains some data, and then at some point, the attacker will start running. Now you may be wondering, why would I share my computer with an attacker? That makes no sense. Well, it does make sense because of cloud computing, right? If you want to use resources in cloud, it's very likely that your program is going to end up running on a data center in some place. And ideally, this is what it would look like, right? You would run your programs in one server, and that is your server and nobody else's. But that's not how cloud computing works. That's the whole basis of cloud computing, right? In reality, you're sharing the server with many other users. You don't really know who's running in there. And so this is the reason why cache side channel attacks actually work, because very often we are sharing our processor resources with other unknown users who may possibly be hacked. Okay, so how does this attack work? Okay, so the attacker starts running, and they're gonna try to fill up the cache with garbage. Anybody care what it is? How do you fill up the cache? It's very, very easy. If you've written a for loop before, you know how to do it. All you need is a for loop, just accessing enough data as cache size you have. And that's it. And then the cache gets filled with junk. Okay. The next step is to let the victim run. Now this can happen either on the same core, or it can happen in the same chip. It does have to happen within the same chip, because you need to share at least one level of the cache, but it can happen in different cores in a multi-core chip. Now, once the victim starts running, and the victim could be running anything, ideally an encryption algorithm, but in this case, a hello world program, who cares? But okay, this is just for illustration purposes. Okay, so the victim runs, and as it runs, it uses some data because we need data to compute something. And as the data is used, it's brought into the cache, and it will change the values that the attacker brought into the cache. Okay. At this point, the attacker, all it has to do is access again the data that it accessed before and time the access to see if the access hit in the first level cache or no. If it didn't, it means that the victim used those slots for its own data. Okay. Now, this is the basics of the prime and probe attack. Now, the key inside of the work that I'm about to tell you is that why are we loading secret information into a shared resource? This shouldn't be the case, right? That's simple logic. So the proposed architecture is, let's just not use caches. Because no matter how you use that, no matter what mitigation approach you use in your cache, the vulnerability still exists. And that's because the fundamental idea that these cache side channel attacks leverage is this sharing of resources, sharing of hardware resources. Okay. So the defense proposed is to not use caches. Now, just simply not using caches would be an idiotic solution because caches help your performance significantly. It's been well established that if you don't use your cache, your performance will decrease like 100%. Okay. Well, all right. So that's a bad idea. So how do we get around that? There's recent technology that has come out of the architecture community called near memory processing. So the idea here is that you're going to have some logic cores near your memory where you can actually do simple computation, and you can bypass the main core. So the proposed defense in this work is basically leveraging that emerging technology, near memory processing, to bypass caches for sensitive computation. Okay. So in this work, we're going to assume a hybrid architecture. And what I mean by that is this traditional microarchitecture that I already told you about with a traditional memory architecture that you may or may not be familiar, but that's okay. And also this near memory processing device that offers a 3D architecture of memory cells paired with logic cores on each of the layers. So this near memory processing architecture, why are we interested in this? Because it allows you to actually use a 3D architecture that builds memory cells with logic cores embedded on the same chip. And that allows you to actually have some simple computations near your memory. Now, it should make it clear, it does not change your memory latency. It changes it slightly, but the biggest component of the memory latency is still there, which is accessing that DRAM cell. So that's not what we're interested in, because we still have this problem of not using caches. But what we're interested in is actually an increased bandwidth that it offers. So if you use this near memory processing architecture, you can actually get a lot more bandwidth out of your memory cell. And if you have a parallelizable computation, then you can actually get a benefit out of using this NMP. Okay, and then of course, in addition, we can get this hardware isolation that we want for security. So in this defense, what we are planning on doing is basically ask the developer to separate their computation into sensitive portions and non-sensitive portions, and then run the sensitive portions on the NMP layer. And then that way we can bypass the cache hierarchy that's usually the target of cache-like signal attacks to minimize this sharing of the sensitive data in the hardware resources. Okay, so to have the developer divide the computation, all we need is to incorporate these keywords into the source code where we expect the NMP computation to start and to end. And then custom compiler basically takes those annotations and splits the computation into two binaries. One will have the computation that runs on the host processor, and the other one runs on the logic core inside the NMP layer. Okay, so then at runtime, when the execution is happening inside the host processor, the binary will contain some annotation that has the address of the function that needs to run in the NMP layer. And then this address will be stored in a shared memory location, and the traditional memory is shared with the NMP device. And so the host core will ask the NMP layer to run this function. The NMP layer will actually read that address, load it into a particular logic core, and then start executing that function. At the end, the function can simply write back into the shared memory location and interrupt the host processor to let them know that the NMP computation is done. At the same time, the host processor can also continue doing other stuff. It's not sitting there waiting for the NMP layer to finish the computation. And so this way, we can actually get efficiency out of the host processor and also separate the sensitive computation out of the main host processor. Okay, so we ran some experiments in a processor simulator. This is usually how you evaluate computer architecture designs. And we found that we ran two encryption algorithms. They're called AES and Blowfish. It's okay if you're not familiar with them. And we ran them with different data sizes. And what we found is that the AES algorithm, which is a lot more parallelizable, you know the word I'm trying to say, it's a hard one. It actually is able to leverage the additional bandwidth to alleviate some of those overheads of not using the cache. So you can see that we get about the same as the baseline performance, and even better at some point when the data is big enough. On the other hand, Blowfish is not as parallelizable. I hate that I have to use that word twice. And you can see the dramatic overheads that we have here. So this work is still not done. There's still a lot more work to do. But this is basically at the point where we actually publish this work. So for now, that's what we have. So if you have a parallelizable encryption algorithm, then you can use this approach to actually isolate it away from cache side channel attacks. And if you don't mind having a 3x performance overhead, you can also use it. Otherwise, you need to find another option. Okay. Any questions so far? Yes.
So, when you were talking about the cache side channel attacks, you mentioned the attacker goes cache, the victim uses cache, and then the attacker can use timing techniques to see which caches were used. Is it like, how does the attacker get any information out of that?
Yeah, that's a good question.
And, yeah.
Do you have another question?
Yeah, and also, since the cache is so small, even if the attacker does get some information from that, isn't it likely that the information is going to be incomplete or broken up or unparsed?
No, so, okay, to answer the first question, there is, analytical work that has been shown to actually be able to extract information out of which sets in cache you use it about the construction of the cache. The cache is more or less like a table with rows and columns. And so depending on which row you use, that row gives you information about the address that you're accessing. And so then for certain encryption algorithms that have, for example, like if this value is a 0 to one thing, and if this value is a 1, different thing, the address that you access is different. And so that's how you can extract information. For the incomplete data, yes, but the attacker is allowed to make multiple probing of the data. And so if the victim is running a long sequence of encryption steps, then you can actually get a lot more data. So yeah, you do need to run the attack a couple of times to get something interesting. Yeah. Good question. Any other? Yeah.
Yeah, I think about how the NFP works. Is it like part of this?
So it's like another memory device, basically. So that's why I put it here on the side. So the memory controller will have a channel for memory, the DRAM, traditional DRAM, and then another channel to the actual end device. So it's like an additional memory.
It would just be connected to.
Yeah, like normal memory. Yep. Okay. In the back and then on the front, and then I'll continue.
So it looks like you're kind of asking the developer to designate like critical sections, right? Essentially. And you said like you could run whatever that is in parallel potentially. But like if we're doing time sensitive computation then there, is there anything that we get to take advantage of? Otherwise we're probably just doing like I guess as well, are we just doing standard like message passing communication, or are we?
You mean between the NMP device and
Yeah.
the CPU? Yeah, just like a message, just like message passing. I guess you're saying like, what if your sensitive computation takes longer, shorter, and then can you get any out of that? That's kind of a different attack vector. So that's more like timing attacks. And you can do something like constant time computations where that should not be an issue, but that's more on the software side of things. And then there was another question. Yeah.
Yes, so in the overhead, do you actually consider the part where you said that the non-sensitive and sensitive data have to be separated by the programmer? So that also adds like a time overhead for the programmer.
Yeah, but that's at developing time, which is not something we care about because we're computer architects. No, yes, maybe, yeah, there's a lot of architecturally secure designs that require the programmer to tell you what you want to be protected. And yes, that has been an issue in the past. So you have a good point, but it's not included in the graph that I showed because this is just showing runtime over. Okay, I'm not gonna take other questions. There's gonna be questions at the end so that I can actually get through my slides. All right. So now we know about cache side channel attacks. We know what they are. We know how we can protect them, but that's not all of it. There's actually an even more powerful attack that has come out in 2018 that affects all processors, and that is transient execution attacks. So now, remember this little diagram I showed you before, we have the cores, the caches, the memory. Now the attack we're talking about, it's mostly at the core level. Okay, so transient execution attacks actually leverage a very, very efficient optimization that has been around for many years, something like 40 years, which is called speculative execution. The reason why we use speculative execution is that we are so good at optimizing our processors, we can actually execute so many instructions at the same time. Sometimes we have long latency events like long memory accesses that prevent us from actually taking advantage of all that efficiency. And so for that reason, very smart people decided that we should do speculative execution. And instead of waiting for those really long events to happen, we should just go ahead and continue running and then let the long events happen in the background. And then if we, for whatever reason, we're not supposed to run those other instructions, we can just clean up our state. And as long as the user does not see any changes, it's all good, right? Our computer architects are magicians. We make illusions of things. We say we do one thing, but in reality, we're doing something else. And it works really well. So the answer to this attack is not simply just turn off speculative execution, because that's not realistic. You guys will not be happy if I turn off speculative execution on your phones. You'll be like, what's going on with this? It crows. Okay, so that's not an option. And kind of the key point of speculative execution that's really important for this attack is the fact that computer architects said, well, what could go wrong? We can just clean up all our architecturally visible state and nobody will know what happened, right? So back then, when speculative execution was designed, the two places where the user could actually see differences were at the registers. That's why I have the core in red, which is where the register file is, and the memory. Now, those two places need to preserve their state across speculative execution, even when we get the path wrong. So that means that when you have a misspeculation, you have to clean up your state and get it back to a place where it was before the speculation happened. So that's all good, okay? The problem is that in this attack, some really smart people showed that caches are also a place where we can actually get architecturally visible state. It's really called microarchitecturally visible state, but the attacker turns it into architecturally visible. Okay, so like before, I'm going to give you a cartoon example of one of these types of attacks called the Spectre Variant 1 attack. This is the one that was published first. It came out in 2018. And even though it was published in 2020, this is a good example of how conference review processes don't work very well. It was an excellent paper. It just took a while to publish. Okay, so here I'm going to give you, again, a cartoon version of this attack just to get you into the mindset of what I'm about to tell you on how to defend it. Okay, so what do I have here? So I have a typical code that any good programmer would write, right? You have an array, you want to access it, you check to make sure that you're in bounds of the array, right? So you're saying if X is within bounds of the array, then I'll go ahead and access it. That's all fine, right? This looks like a perfectly fine code. Now, on your right side, it would get confused left and right. You have the more or less high-level architecture of what's happening with this code and data, okay? Now, this perfectly fine code is actually what's going to trigger our speculative execution. The attacker can actually force this line to actually become a really long line because we have array size, which is actually data and memory that we have to access, and we have a comparison with that value. So the processor will first need to bring the array size onto a register to then compare it to the value of X. The attacker can then use another very efficient optimization, the branch predictor, to train the processor to think that that if statement will always be true. How does it do that? Very simple, again, a for loop. You know how to write a for loop, right? Everybody does. Oh. So you write this for loop, you call this function many times, and you teach the processor that every time you call this if statement, it will be true, okay? This will adjust the branch predictor to say this particular if statement is always true. So what's gonna happen is then the attacker will force this value to be out of the cache hierarchy. And you already know how to do that because I show you the code on how to load junk onto your cache. And we're just gonna force it to be in memory. So now what's gonna happen is that when the processor starts executing this line of code, mouse is kind of delayed here, okay. So when the processor executes this line of code, it will say, oh, I need to go get this data from memory. So that's gonna take me a really long time. But in the meantime, I've seen this if statement a million times. I know it's gonna be true. So let me just go ahead and go inside the if statement and continue executing these instructions. Okay, so it goes to the next line. And it says, okay, array X, yes, I know that. I know the array base, I know X, I'm gonna add it. And look at that, the value is in my cache. So that takes no time. That's all fine. So now we can use that value that we just fetched to access the second array. And it doesn't really matter where that second value is. It can be in memory, it doesn't matter. The fact that this line will actually execute will prompt the cache hierarchy to bring that value up into the L1 cache. And then at some really long time later, the processor will say, oh, wait a minute, X is not less than array size in this case. X is some other value, and I shouldn't have gone into this if statement. Now, what happens now? This is a misspeculation event. So the processor will flush the pipeline, it will flush all the states that it created, and then resume from where it was supposed to be, which is the else statement or outside of place statement. Okay, so where's the attack? What happened? Well, the fact that this array2 of the secret is in the cache reveals actually the value of the secret, because I already showed you how an attacker can actually access data and take the time to see how long it takes to access a piece of data. And all the attacker needs to do is access an array2, all the items of array2, to see which item is in the cache and which are not. The item that's in the cache will reveal the secret value. So it's even an easier attack. Okay. So what is the key insight here? What we saw, there's many variants of this attack that I just showed you that vary in multiple ways, but there's one thing that they don't vary on, and that is that all the attacks involve one really unusual access, that secret access array of X, where X is the value of the secret. And so you can actually identify the attack based on the memory trace. And so the proposed defense that we have here, we call it SMAD, it stands for Secure Memory Access Design, is that if we put basically a monitor in the processor to see if the memory access is unusual, then we're not going to let it execute speculatively, okay? And the concept here is that we don't want to turn off speculative execution. We only want to turn it off when it could be used maliciously, okay? And so when X is the value that it's supposed to be within the array size, we want the processor to do speculative execution, because that will give us a big performance improvement. But when it's not, which is not even meant to execute anyways, then we don't want to run it speculatively. Okay, so now I'm going to change the diagram a little bit. We implemented this depends on an article for processor. So I'm going to give you a very quick review of out-of-order processors. This again is a very simplified version. In out-of-order processor, these are the different stages that you have on the processor. You have fetch, dispatch, issue, execute, complete, and retire. The ROB stands for reorder buffer, and that's where the instructions wait to be executed. The parts in blue happen in order, in program order. The parts in red happen out of order. And why am I telling you about this? Because I need to tell you what components you need in order to actually implement the SMAD design. Okay, so the first thing we propose is we need to identify the safe regions. We need to know when we need to not, or when we can execute speculatively and when we shouldn't. And so we need this little table that will have the safe regions for multiple different sections. Now, why do we need a table and not just one register? Because, like I said before, processors can actually process many instructions in parallel. And so we want to be able to define many different safe regions in parallel. That's what we need a little table. Then we need a dispatch time. And the reason why we do it at dispatch time and not another stage is that this is an in order stage. And so we want to, in order, assign the safe region that's supposed to go along with the memory operation. So we enhance the dispatch stage to actually do this check. And then we also enhance the reorder buffer to have two things. The first one is the SRHB ID, so that you can track the instruction with its ID. And also a 1-bit to indicate if the instruction is safe or not. So, and that's going to tell us if we can execute it speculatively or not. Okay, so then we need to enhance the issue stage to check both if the SRHB entry is ready and also if we are within the bounds or not. Okay, so if we're within the bounds and the SRHB entry is ready, then we can actually execute speculatively. Okay, so this is kind of how you implement SMAD. So I'm going to have little animation and to show you exactly how it works. So we have a memory operation, and this only happens with memory operations. When it gets to the dispatch, it will check the tail, the current tail of that buffer. It will assign that ID to the metadata of the instruction, and then it will store that into the reorder buffer. And then at some later point in time, when the SRHB entry is ready, notice that ready did again, the instruction will actually be issued. And at this point, we are going to be able to check if the bounds are met. So if the address location is within the safe region of that particular entry, then we're going to say that this instruction is safe and it can execute speculatively. And so we're going to go ahead and let it execute and complete. And these are all the stages of an out of order processor, and everything's good. Now, in the case of an instruction that is not safe, so that is where the address does not fall within the safe region bounds, then the safe bit will be set to 0. And then instead of letting the instruction actually issue, it's going to have to wait in the reorder buffer until it becomes the head of the reorder buffer. And at this point, the instruction can no longer be speculative because it is the oldest instruction in the processor. And so at that point, the instruction becomes safe to execute, not speculatively, and it's issued and executed and so on. Okay. All right. So I purposely did not tell you how we're defining safe regions, because we are saying that you can actually define the safe region in multiple ways. The initial approach we had was to define it as a stack frame. So if you remember your memory layout, your virtual memory layout, where you have your stack and your heap and your code and your text, your stack frame is supposed to be your most fresh memory and the one that you're supposed to use. But we found that that wasn't so efficient. You still have some overhead. And so instead we look to do other things. And so one way is to leverage other secure architectures that actually have isolation of memory regions. And so we can use that. But a better way is with this new custom instruction that we're proposing called SSMR, Set Safe Memory Region. Everything has to have an acronym. Okay, so we also propose with that, besides this instruction, a compiler pass that will be the one responsible to inject this SMR instruction automatically. We're not asking the user to do it because that would invite a lot of other vulnerabilities that it's just a can of worms I don't want to open. So instead we propose that this instruction is exclusive for the compiler to be out. Okay, so the instruction basically takes in one input register, one immediate. It actually sets the lower address of the safe region as the value of the register, and then it adds the size to calculate the end. And the way that it would look like, this is kind of an example of one of our tests. After we push it through the customized compiler, it's basically we'll find all the memory operations and then also tie it to the variable definition to know how big the variable is, and then assign the SSMR instruction with the correct size. Okay, so now back to the little cartoon. How does the SSMR instruction work in the processor? So you have the SSMR instruction like any other instruction. It's get fetch. At this batch, it's actually allocated an entry into the SRHB. And then when the instruction gets issued, it's actually when the SRHB entry is actually set and the ready bit is set. And then everything else happens as I showed you before. Okay, so that's basically SMAD and SSMR in a nutshell. All right, so we compared the security of SMAD and the performance running the design on a processor simulator again. We used M5. We ran it with several benchmarks, and what I'm showing you here is a geometric mean of those benchmarks. And so we have the cycles per instructions if you're not familiar with CPI. So these are how many cycles per instruction you have. Ideally, you have at least one. And so in the blue bar, we have the baseline without the SSMR instructions. In the yellow line, we have the baseline with the SSMR instructions. So basically the modified program, but with the SMAD defense turned off. So the pink bar, you can see that's using the spec frame as a safe region. It's not as good as using the SSMR instruction, but both of them do not have such large overheads. So 23 and 19% is the transient execution attack world. It's actually a really good overhead, believe me or not. This is actually equivalent to state-of-the-art defense mechanisms. And not only has equivalent overhead, but it also is able to close some vulnerabilities that other defense mechanisms cannot. So that's kind of the key point. And the reason that we're able to do this, where all the dots are filled, is that we're actually targeting the fundamental property of processors that this attack targets. I am going to not accept questions now so that I can finish in time. Try to finish in time, and then I'll take questions. I'm happy to stay a little bit over time. Okay. So the last work I want to tell you about is spec check. Besides being able to defend against attacks, we also are interested in developing technologies that can let us measure security. Because without this measuring tool, it's very easy to put security in the backseat and not care about it, which is what has been happening and why we're here today. So I collected a little bit of data over a bunch of papers that I read on the topic of architectural security. And I noticed that for the security evaluation, in most cases, all we have is a discussion section. This is secure because we secured against this attack. It's kind of a well-being logic. In some cases, the attack that they're trying to defend from is implemented and they show that it's actually patched. But that's kind of a narrow view. Like, what about other attacks? And what about other things that perhaps you didn't consider? So we think it's really important to develop an infrastructure that can let you measure security. And key insight in this work is that commonly used processor simulators already have all the information we need to identify attacks. And so we're basically going to leverage that to develop an infrastructure that can let us identify potentially vulnerable sequences of instructions. So the transient execution attack that I just showed you can be basically summarized into these 4 steps. Again, this is the same code, more or less the same code that I showed you before. And it's basically doing inducing speculation with that if statement, transiently loading the secret by doing that array to access, transiently transmitting the secret, loading the secret, the first array access, transiently transmitting the secret, the second array access. Now recovering the secret, I'm not showing you the code here, but it's a simple cache site template, which I did show you before. Okay, so with those 4 steps, what we care about is how can we map the information we have from the processor simulator into those 4 steps. And I'm just showing you a snippet of the output that you could actually get out of this processor simulators, which actually tell you the state of each instruction that is executing for the processor. So for example, the information on the retire stage, which tells you if an instruction completed or not, tells you if the instruction was misspeculated or not. The instruction itself, the assembly code, tells you what instruction you have and if it's supposed to have a microarchitectural physical state. The actual arguments for the instruction itself tells you if it's actually a secret that was previously loaded or not. And then this information about the complete stage tells you if the instruction was actually executed or not. So will it have an effect on the cache? And so that's basically what we leverage to construct this spec check infrastructure. And we map it to a finite state machine because that was the easiest way to actually make sense of it. And so we actually constructed a finite state machine that defines a transient execution attack. And so here I'm just giving you a small example of how the finite state machine works. So as long as an instruction is retired, we stay in the initial state. When we see an instruction that's flushed, basically the retire stage is 0 input, we go into the first state. Then if we see an instruction that's not a load, not a memory operation, then we stay in the same state. And otherwise, if the instruction retires, we go back to the initial state. This is the full finite state machine that describes the transient execution attack that I described before. And basically, we implemented this finite state machine on this processor simulator to identify when we end up in a vulnerable state that could potentially be an attack. Now, this finite state machine requires this microarchitecturally visible property, which we think is actually a property of the ISA, the instruction set architecture. So we think that this should be part of the ISA definition, so that if you have an instruction that has microarchitecturally visible state, it should go along with the instruction. So for example, we already know that memory operations, control flow operations, and floating point operations all have microarchitecturally visible state. And the ISA developers are in the best position to make this determination. So that's why we claim that that's where it comes from. Okay, so we implemented spec check, and for the sake of time, I'm gonna rush through this slide. We implemented it on top of Gen 5 with these 5 design principles. We basically wanted to make it consider both software and hardware. We wanted to make it accessible. We wanted to use tools that are already used in the research community. And so all of these were design principles of spec check. Spec check is the little funny hat in the middle. So with Gen 5, it is a processor simulator we use. You feed it a program and you feed it a configuration definition, and then you run the experiment. And spec check is kind of a monitor that's constantly running. And then at the end of the experiment, what you get is not only the traditional metrics for the processor simulator, but you also get the vulnerable PCs that spec check found. So we ran two very well-known attacks, and on both attacks, spec check was able to identify the exact program counter that is vulnerable, and it did not report any false negatives, so it didn't think that an attack was not vulnerable. And then we also ran several well-known benchmarks, and we found that under 25% of the speculated regions were vulnerable, which we don't know if they're really vulnerable. We would have to actually go into the code and really look deeper into that, but we think that 25% is a reasonable number. All right, I made it on time with 5 minutes for questions. So this is the summary. Again, I'm not going to rehash so that I can take questions. I should say all of this work has been done not by myself, with my collaborators, my students. So I should thank them for making it possible. And now I will take questions.
Spec check, or,
Yeah, I have a summary for questions.
yeah, with spec check, is that something that could be, our software or ETM? Like, what's the application?
We designed it more for computer architecture design, like a research design. So we designed it on top of a processor simulator more than that. That is a typical question we get. Why not just make it into a defense? And the reason for that is that spec check needs kind of an omnipotent view of the processor, which if you do it at one time, it may already be too late for the attack. The attack's already happening, can't do anything about it. So that's why. So,
Here, you guys,
yeah,
stay
quiet.
quiet, please, and also for Zoom, thank you.
So the target application for this type of framework is for either like companies like Intel in AMD, the design processors, to make sure that their designs are not vulnerable. But also for researchers like me who maybe come up with some design and, you know, I want to make sure they didn't mess up with some defense that, you know, maybe makes it vulnerable to transient execution attacks. We implemented it for transient execution attacks, but we envision this to be expanded to other attacks as well, to be more comprehensive. Yeah, thank you for the question. Other questions? Yes, Ken.
Yeah, for the transient execution attack, I saw that it was focusing on statically allocated arrays. Is that because the attacks rely on statically allocated arrays? Could this transition be based?
It can transition to heap-based, yes. It's just easier to reason about it when you're explaining it, but yeah, no, it can definitely happen with any type of array. Yeah. Okay.
I don't have a complete understanding of this. There was a point brought up that like in the cloud server that we may have two VMs and running on a multi like the shared tenant. And one VM may be like the attacker may be running the their code there and then we may be able to the other VM can be able to, right? But isn't it like the hypervisor would kind of like give a separate page table for both of the VMs and the operating systems would be like kind of like work on an isolated way, but how is it like can access the same shared caches?
Yes, that's the illusion that I was telling you about. Yes, you think you're in separate machines, but you're not. Yes, you're in hypervisor, you're in a virtual machine, but under the hood, the hardware is the same. Right? Even if you have different page tables, even if you have different operating systems, the hardware you're using is the same. Doesn't matter where you are. I didn't give you a very satisfying answer. You don't believe me. I can show you.
I don't understand. On the shared space, but I thought like we will be able to access. There is some kind of like you wouldn't be knowing the.
So you wouldn't be able to access the data directly, right? You're not accessing the data directly of other countries. What you're accessing is the same cache, the same host, right? It's not a software construct, it's hardware. It's a physical machine. Okay, I'll move on to another question. Yeah.
Actually, I have two.
Okay.
In modifying power plants, like, So did they? That's the thing.
No. No, and because of the timeline of research. So usually when you come up with a really great idea, it usually does not go into a processor for another 10 years. And that is if you're lucky. It actually goes into the processor.
Is it correct to say that water time is basically one of those stuff?
Oh, absolutely.
Like micro.
Absolutely. Yes. There's been some defense mechanisms that have been implemented, but they're not bulletproof. They're definitely vulnerable.
Just
Mhm.
also for this balancing. Can you directly access the whole?
Yeah, every time you're running a program, you're accessing the O1 cache.
But literally, can you like target it?
Right, you're not looking at it like I'm showing you on the slide. Yes, you're right about that. You're just accessing an address. But you can actually time each access you make and then derive the row that you're accessing based on the address you're accessing. Yeah, other questions? All right, well, I'll stick around for a couple of minutes if you have more questions. Thank you, guys.